are yours. Okay, great.
Well, thank you for inviting me. I'm not usually used to using a microphone like this, so I'll probably forget a few times. So, why is it working? Do I have to do something special?
That's fine.
It's working.
Okay, good. So why have I been doing distributed ledger technology for my teaching for the last 5 years? It turns out that I had a 7-year hiatus from teaching. I usually teach international finance, advanced asset management, stuff like that. But 7 years I didn't teach because I was editing the Journal of Finance, and it's a full-time job. So after the 7 years, I went back to my international finance notes and decided to scrap them and start again. So I thought my students would appreciate that rather than me pulling these old slides from 7 years ago. And when I did that, one of the common things that we do in international finance is FX. And I thought maybe I could add something different, something on cryptocurrency. So I dove into this sort of Bitcoin world to put together one lecture. Most of my colleagues thought I was crazy because it was just a fad. And it went really well for the students, like really well. They encouraged me to do a whole course on it. So the next year I prepared a full course. And it was a very interesting course where I had computer science specialists, engineers, law students, business students all together. And then the course grew and grew. It went from 13 students to 40 students to 75 students. This year, 231. So over half of the MBAs that graduated at Duke this year took my blockchain course. And the course is basically designed with a number of goals: a technical understanding of blockchain technology, and also it's called Innovation and Crypto Ventures. So the students need to actually put together a venture idea, a pitch deck, 15-page pitch deck that they will basically present the last day of the term. And that's their grade. So in order for them to start working on that immediately, I need to do a tour of the technology in the first hour of the course. And that is what I'm going to do right now. And I say that I can hopefully take people to the 1% of blockchain knowledge just in this 1 hour. So the hour is pretty mild on technical detail. I will have the slide deck circulated that also has links to my course. My course is, everything is available for anybody. It's wide open on the internet. The course, basically, I do this 1 hour introduction, then dive into the details. And this is probably, for my students, the most technically challenging course that they do in their MBA. Indeed, there's an individual assignment where you have to deploy a smart contract to the Ethereum blockchain. And that's pretty shocking in terms of the usual perception of MBAs. So let me go, and part of the goal of this presentation is to link to the stuff that we do at Man Group, but also just to give you a perspective on all the possible applications. So I'll talk about some applications that are not directly applicable to what we do at Man, but you might see in that application something else that might be relevant indirectly to what we do at Man Group. Okay. The other goal indeed of my course is to separate out the people that think they know something about blockchain technology from the people that actually do know something about it. So and I basically show my students examples of people saying stuff that just blatantly false. And it reveals that they don't really understand the technology. And we'll do a few of those things today. So let me start and start right at the beginning. So one of the myths about blockchain technology is that it was invented by Satoshi Nakamoto, the person supposedly that invented Bitcoin. So that's false. You see it all the time where people interchange Bitcoin and blockchain. Blockchain's a technology, and there's many different ways to implement the technology. Many different ways. Okay, so Bitcoin is an application of this technology. This technology invented by Haber and Stornetta in a paper published in the Journal of Cryptology in 1991. And their idea was motivated by the timestamping of digital documents. So as you know, you might have a Word file that's got a date on it, but it's fairly straightforward to manipulate that date. So what they wanted was a method to kind of prove the date of a document. And that application is still a highly relevant application for blockchain technology today. So it turns out that this paper didn't get much attention in 1991, but after Satoshi Nakamoto's paper in 2008, it began to get a lot of attention. Okay, so I would say that Bitcoin was a great first application of blockchain. My course, probably only 15% of my course talks about cryptocurrency. My course is interdisciplinary, and we deal with operations, accounting, marketing, all this stuff that potentially is disrupted with this technology. Okay, so let me describe the basic idea of this technology. So the first thing is that this is a distributed ledger. So think of a blockchain as a spreadsheet, but it's not centralized. It resides on many different nodes. So these dots are nodes, and like the internet, this is a distributed technology. That is very important for this because if there is an attack on the network survives because there's no one copy of the ledger that can be hacked. Number two attribute is transparency. And most of the big blockchains like Ethereum and Bitcoin are completely open. So anybody can download the entire Bitcoin blockchain, and it is in plain text, right? So you see all of the transactions, and anybody can look at that. But that is a choice. And I'll describe a few blockchain applications where there's various different levels of transparency. So number three is perhaps the most important attribute, and that's immutability. So once you put something in a blockchain, it's there forever. So if you make a mistake, well, too bad. Perhaps if you make a mistake, you can negotiate with the other party and do a reversing transaction. But again, you would see both transactions, the mistake and the reversing transaction. So immutability is very important, and I need to prove to you that it's really unlikely that you can alter history. So nothing is impossible, obviously, but the idea is that this technology makes it very difficult to alter history. And number four is the cryptographic security of this particular system. So instead of having one spreadsheet, think of it as many subsheets or blocks. And these subsheets are connected, and that's the chain part of it. And it turns out that the last line of one block is the first line of the next block. So that's why it's called blockchain. And you're going to see this diagram 3 times. And each time I show it to you, I'll tell you a little more about the diagram. And by the third time, hopefully, it's very clear how this system actually works. Okay, so what does blockchain do? I view it as doing two things. So number one, it provides a way to verify ownership of something. So think of this ledger that is immutable, that people can't go edit, whether it's a nefarious party, whether it's a government. It basically proves that you own something. The ledger can be consulted, and there it is. It's set in stone. So verification of ownership is the number one attribute. The second thing it allows is the efficient exchange of ownership within this technology. So a new transaction actually goes in to transfer ownership from one person to another, and then all of a sudden we've got verification of the ownership for the new person. Let me start out with some examples, a finance example. This is a picture of the New York Stock Exchange in the 20s. In 1920s, to settle a stock trade took 5 days. In 1995, there was what the media described a revolution in technology where we moved from T+5 to T+3. And this is the time where, World Wide Web existed, and they're bragging about 2 days to settle a stock transaction. It turns out that September 7th, 2017, it continues, this great technological advance. Indeed, it is described by FINRA as a new era in security settlement. So we go from T+3 to T+2. It's almost comical to me. Why do we have to wait 2 days? So this technology allows you to do a settlement in a matter of minutes. So the stock exchange that's heavily invested in this is the Australian Stock Exchange. And they will go live 100% blockchain, and their target is April 2021. Okay, so they're the 10th largest exchange in the world. Everybody's watching them very carefully. Look, all the major stock exchanges are they realize that this is where they must go. And Australia being the 10th largest, good place to actually test this out. So we will see, in my opinion, it's my forecast, which I've got a large amount of confidence on, all stock exchanges in the next decade will be 100% blockchain based with instant settlement. Okay, here's a good example of verification of ownership. One of the issues in buying property is you're not really sure the person you're buying the property from owns the property. So often you need to hire a lawyer to do some sort of title search. So think of a blockchain-based construct where there's a ledger and it's got a record of who owns all the property plus all the liens on the properties within, let's say, a municipality. So it's very simple. You don't need the lawyer to do the search. You've got this construct. You can see who actually owns the property. In the U.S., to get a loan or mortgage, you have to pay title insurance. So title insurance basically protects the bank from the situation where they lend you money and you pay it to the person that you think owns the property, but they actually don't own the property. So all of the people doing title insurance will be out of work with this technology. There are some countries, some smaller countries, that have already begun the process of putting every piece of land in the country into a blockchain construct. Okay, so this is definitely for real. SWIFT. SWIFT is a dinosaur technology. It's just a matter of time. It's constantly under attack, this messaging system. This is basically going to be disrupted with blockchain-based payments that are much more secure, they're instant and very cheap. Counterfeiting This is the most counterfeited currency in the world, and for some countries, it's a national source of revenue. Again, think of this technology as enabling the serial number on the currency. Take it seriously. Right now, we don't. So I'll talk a little more about a national cryptocurrency a little later on. Okay, here's another verification of ownership. You get into your car, and instead of using a key, and frankly, the actual car key, it will be like a museum exhibit. Right? It just doesn't make any sense that in the future we'll have these physical keys. So you get into the car, you do a scan or thumb or fingerprint, a blockchain is checked, you're the owner of the car starts. A very simple sort of verification. And indeed, rental car companies are investigating this. So you rent the car for a certain period of time, and only you can start the car, or somebody you designate to start the car. Let me change the example a little bit. So suppose I bought the car, but I financed the car with a loan from the bank. In that contract, it says that if I miss 3 monthly payments in a row, then I'm in default. So I get into the car, I do the scan, I've missed 3 monthly payments in a row, doesn't start. It starts for the bank, though. Okay, so that is an example of a smart contract. Okay, so a smart contract is a simple if-then statement. And usually it's coupled with what we call an oracle. So you get into the car, and essentially and you do your scan, and then that triggers going out to find a piece of information externally, outside of the blockchain construct, and that is your payment history on this loan. And it's a simple if-then statement. And again, that is possible today in a number of blockchains, especially the Ethereum blockchain. So this technology is a P2P sort of technology. Indeed, any situation where there's a thick layer of middle people, then you will have a situation where potentially a blockchain application could be very disruptive. There are many different ways to implement blockchain. So, and again, people get basically confused by this. So, for example, this is one of my the assignments for my students were there was a conference at Duke. And one of the panels was on blockchain, and there are 4 so-called experts. And the assignment was basically to write down every false statement that these experts made. And there were a lot of them. So one of them said, oh, well, blockchain's not going anywhere because of all the power it uses. So, well, that is true for some blockchains, like Bitcoin's blockchain, but is not true for other blockchains. So again, this idea of confusing the Bitcoin blockchain with blockchain technology in general. Indeed, you can have a private blockchain where the only people that can write to the blockchain are permissioned to do that. And there's no issue about the power consumption. Okay, so this, again, there's many different types of these. So I'll spend a little bit of time on Bitcoin, given that it was the first big application and it is the most prominent type of blockchain. So, and I'll try to walk you through this. Again, anybody can download the Bitcoin blockchain, and there's a computer program that goes along with it that you need to be running to basically keep up to date. Okay, you turn your computer off, then when you turn it back on, basically the new blocks that have been added to the blockchain are put on automatically. And again, the computer program is doing various things. So the security for this blockchain is provided by a group of people called miners, and I will show you what they actually do in a few minutes. Okay, the first thing that's really surprising is the amount of computing power that's devoted to the Bitcoin blockchain. So if you think of the world's fastest supercomputer, that's the IBM Summit as of June 9th, 2018. And it runs at 3,300 petaflops. So floating point operation per second. And a megaflop is 1,000,000 operations per second. So go mega, giga, tera, and is there something before peta? I forget. There's a lot of operations per second. So supercomputers at 3,300, the Bitcoin network at 80 million. Okay, so it is a very large amount of computing power that's distributed all over the world. I need to show you what it's actually used for, but it is basically so large that for somebody to do something nefarious, they would have to have a budget of at least $3 billion. And it's not like you can just order this stuff easily off of Amazon. These are very specialized chips that are manufactured for the job of the security of this blockchain. Okay, so basically who can cause a problem? Maybe a nefarious state actor like Russia or China. North Korea doesn't have the money to do this. Maybe they can print fake US dollars to do it, but they're just not in a position to do this. And even after doing this, you can disrupt the current transactions. It's very unlikely you can go back in time and rewrite history. Okay, so again, I need to prove to you. So this is a staggering amount of computing power. So let me get into some of the mechanics. I know many of you kind of know this stuff, but I want everybody to be on the same page here. So the first thing that's kind of important to this technology is the idea of cryptographic hashing. So let me do a very simple hash for you. And this is the issue. I need to send an email to Danielle. The very simple email, but we're both worried that the emails can be intercepted and altered, okay, by a nefarious person. So we come up with a system. And it's a really simple idea. What we're going to do is assign letters to numbers. So A is 1, B is 2, Z is 26. And this is message very simple, only one word. All we're going to do is to multiply all those numbers together. And that's going to be my cryptographic hash. Okay, so I do that. And the word hello, which is my message, is 86,400. So I send the email to Danielle. Danielle knows the hashing function. So she gets the email. She does the hashing function and gets 86,400. She checks my website where I posted that number, 86,400. It matches, and we're confident that the email has not been corrupted. So if it was altered, perhaps corrupted, so instead of hello, it's hallo, H-A-L-L-O. Then when Danielle gets that, does the cryptographic hash, she'll get 17,280, and that doesn't match. We have to try again. Okay, so this is a very simple system, and the hashing function I'm suggesting is not a very good one, because it's got the problem that if you reorganize the letters, you get the same hash. So let's say I'm a nefarious actor. I altered the message from hello to oh hell. Much different meaning. But because the same letters are used, you get the 86,400. So when two different messages deliver the same hash, that is called a collision. Okay, so what we need to do is to find a function that will not have collisions. And that function is going to be a SHA-256. Secure hashing algorithm 256. It's 256 because the output is 256 bits, zeros and ones. Okay, so it doesn't matter the size of the input. It could be a single letter or number, or it could be something very large. The output is going to be 256 bits. This, and again, this is maybe we should keep a list of these things, but don't confuse this with encryption. It is a cryptographic hashing function, but it's not encryption. So with encryption, we take a document, we encrypt it with a key, and then we can decrypt the document with a key. This is a one-way function. So you get this representation in 256 bits, but you can't go the other way. Indeed, think this is a good way to think of the intuition here. Suppose you drag a 9 gigabyte movie into a hashing function, and it delivers 256 bits. Does it make any sense that you can somehow invert the 256 bits back into the movie? I don't think so. So it's one way, and it's designed to do that. And what I'm going to do is to hop out to the internet and actually show you how this works. It's going to be challenging given the size of the screen, but there's many online calculators, and I just typed in "Hello World!" ! And I will do the hash, and I'll read it out for you. It's represented not by the zeros and ones, but in hexadecimal form, just for presentation purposes, and that's 0 to 9 plus the first 6 letters of the alphabet. So it's base 16. So it's 64 numbers and characters. And Hello World is 315 F5, the first of 5 letters of the cryptographic hash. Now let's suppose I put a 0 after this, and it's completely different. So it's not just changing the end of it, it's totally different. So it starts 1312 AF now. So completely different. And to prove to you that it's not random, let's go back to the original one, and we get 315 F5, exactly what we had before. I'm going to do one more, and I'll put a number 4250 and do the hash. Notice this one is a little different. It's got 4 leading zeros. Okay, that's rare. So the probability of getting a 0 is 1 over 16. The probability of getting 4 in a row is 1 over 16 times 1 over 16 times 1 over 16, 1 over 16. Okay, indeed, I had to try a lot of numbers after the Hello World to get those 4 leading zeros. I didn't do it manually. It was some Python script that I ran. But the idea here is that you'd have to try a lot of numbers to get this, this particular hash. Okay, so let's go back to the presentation. And now let's go back to that email problem that we were, the email to Danielle. And now what we're going to do is I'm going to send the email to Danielle. I'm going to do a SHA-256 of the text, post that on my website, and then she receives the message. She does the SHA-256, checks to see if it matches, and we're done. There's no collision. Okay? Indeed, this is how email works. And indeed, if you go into your Outlook and look at the full header of the email, which is very long, actually, and you're going to see SHA-256, you're going to see SHA-384, which is just 384 bits rather than 256. So, let me just qualify one thing. Remember I said that it's really, I might have said impossible to invert the hash, right? So you put the movie in, it's 256 bits. Can you actually get back the movie? And it turns out you can. It's just really improbable that you can do it. So the only way to do it is brute force. And to brute force get back that movie, the number of guesses is very large. So it's on the order of the number of atoms in the known universe. So nothing is impossible. It's just extremely improbable to actually undo this. I can't resist. This is the last kind of hashing thing. This is during the U.S. election. And it was Trump versus Hillary Clinton. And Clinton's campaign chair, John Podesta, his emails were hacked. And WikiLeaks began to post his emails online. So the head of WikiLeaks is actually held up in London, right, at the Ecuadorian embassy. So he's basically wanted in Sweden, and he's been in that embassy for years, it seems. So as soon as they started to post these emails from the Clinton campaign, the internet was cut at the Ecuadorian embassy. Probably the US government behind that. So WikiLeaks sent out 3 tweets, and I've reproduced one of them. And the Wall Street Journal, which I actually think is a pretty high quality media outlet in terms of the quality of their reporters, but they're not alone. Basically, everybody was reporting the same way that the Wall Street Journal was. So it says that 3 messages over Twitter, each one began pre-commitment, and then the number 1, 2, or 3. So we see pre-commitment 1, John Kerry, followed by short phrase, which is John Kerry, and then an assortment of 64 letters and numbers. So you know now, just by eyeballing this tweet, you can see the 64 letters and numbers are hexadecimal. This is a SHA-256. So none of the media outlets actually got this. But in my course, my students felt very empowered because they totally understood what was going on. So why would WikiLeaks send out a SHA-256 with John Kerry's name on it? So I'll tell you what was happening. John Kerry's Secretary of State, and they were scrambling in the State Department to do SHA-256 hash of all the crucial, confidential, secret documents. And they stopped when they found a match, and they knew that WikiLeaks must have this document. If they've got a hash of it, they've got to have it. So basically, WikiLeaks was saying, hey, we've got this document, and we're going to make it public. You better turn back on the internet. And they did. So this is a story that has not been told, and it's just an application of this technology. Okay, so this is the second time you've seen this diagram, right? The blocks with the linkages. Remember I said the last line was the first line of the next block? The last line is a SHA-256 of all of the data in this block. Okay, so it's the last line and the first line. And if somebody alters, even in a very subtle way, any data in this block, it will produce a different SHA-256. That will not match the next block. So if you go back in history and make a change, ever so subtle, no match. Indeed, I've got an example. This is not with the SHA-256 because there's too many characters. It's a simpler hash. But here's 3 blocks. A hash of this block is the first line. The hash of this block is the first line. So they're all connected the way that I'm describing. And there's a transaction in block 1000 that is actually, I'm involved in it. I buy a car from John. I pay John 17, and I get the car. So I figure maybe I'll do something nefarious. And the next thing, you can barely see the difference in my nefarious action. Kind of looks the same. All I've done is to flip the signs of the transactions. So now, instead of me paying John 17, John pays me 17. I get the car and I get the cash. So obviously a good deal for me, but what happens when we do this? So all I did was to flip the signs, a negative to a positive. And when we do that, the hash is changed and it doesn't match the next block. The network, so all these nodes are running a program that's looking for stuff like this. So it's constantly checking to make sure that the linkages, the chain is secure. The network throws out block 1000 on a particular node, my node, and replaces it automatically with the block that actually has the connection that works. Okay, so this is a very powerful idea that somebody can attack the history, make some alterations in perhaps many different copies of the ledger, and the network is going to see that those alterations change the hash. It doesn't match. They'll find the block that is valid, automatically replace, and we move on. Okay, so there's one more thing. And this is the third time that you're seeing this diagram. There's one thing that's kind of missing. And that is that maybe I can go back in history and change a block, but then also alter all of the future blocks so they actually do match. Okay, so that's going to be an issue. So we need to make it very difficult for somebody to go back in history and do that. So this is where the miners actually come in and all of this computing power. So what the miners are doing is validating the transactions. And when I say validating, it means that you're buying something, you need to actually have the money to buy it. So you can't spend what you don't have. So they're validating the transactions, and then they're doing a SHA-256 of the transactions, but they do something else. And that is they take all these transactions, and then they add a number called a nonce. And I actually was doing the same thing with Hello World. So I put a 0 there. And I could put a 1 or a 2 or a 3. And then I put that 4250 and got the 4 leading zeros. Well, this is what the miners are basically doing. They're cycling through numbers to try to get a lot of leading zeros. And it turns out that the number of leading zeros that they've got today, 18. That's where the computing power is actually coming in. To get 18 leading zeros is very improbable. Okay, so the big lottery in the U.S. is called the Powerball, and it's very improbable to win. The probability of getting the 18 leading zeros is close to the probability of winning this lottery twice in a row. Okay, so there's a huge amount of hashing actually going on. So basically, again, you take the same data, the transactions, you add a number, you try to see if you get a lot of leading zeros. Most of the time you don't, and you have to keep on cycling through. And the chips, the specialized chips, they've got one purpose, and that is to do a SHA-256. That's it. Okay, so that's what the miners are actually doing. And right now, the hash rate of the network is 50 billion gigahashes per second. And a gigahash is a billion hashes. So 50 billion hashes per second. So again, if this network was a country, it would be the 61st largest country in terms of the energy consumption. Okay, so that's a lot of computing power. You might wonder, well, what if there's an innovation in computing technology that makes it much faster to do one of these hashes? Well, that's no big deal, because in the computer program, it says we want to add a new block to the blockchain associated with Bitcoin every 10 minutes. So if it's the case that blocks are being added every 5 minutes, the computer program switches and makes it more difficult. So think of it as adding another 0. Since instead of 18, you need 19. And it's the same thing if computing power goes off the network. Then the difficulty goes to something like 17 or 16. The point here is that given these blocks are added every 10 minutes, it makes it extremely improbable that you could go back in time, change a block, and then basically solve all of the future blocks again and alter history. It's just not feasible to do that given the amount of computing power. So that's the last part here, and that's why we need the computing power to secure the immutability of property. Okay. I know JP Morgan has been in, and let me just talk a little bit about their idea. So one issue with, let's say, the Bitcoin or Ethereum blockchain is completely transparent. And that's going to create a problem for a lot of stuff that we do. So, for example, Bank A might do a transaction with Bank B. Does it make sense that all of the other banks get to see that transaction? Probably not. So is there a way to use this blockchain technology, but to have it done in such a way that it's not transparent to people outside of the transaction? So the idea of quorum is very simple. We'll take a contract between two parties, A and B, and it could be very general contract. It could be a trade or anything like that. So think of this in the most general way. Between, let's say, A and B, and then what we're going to do is encrypt the contract. Okay, so encryption means that there are keys that can decrypt the transaction. So party A has got a key, party B has got a key. The encrypted contract goes into a blockchain construct. So it's there, it's set in stone forever, and the parties that are involved in the contract get to see the transaction. Other people don't see it, but it's there in a secure place, and it's there and immutable. Indeed, there could be a third key for the regulator, so they get to see the actual contracts. Okay, so this is a very interesting idea, and I think JP Morgan is very keen on this because it's got this ability to make the back office function much more efficient with this technology. And I know when they pitched the main group, I was there for their pitch, and they're thinking like two things. Number one, they're thinking of saving money at JP Morgan, and number two, they're thinking of saving money with their clients, so or the people they do business with. So that is one of their initiatives. They also have a number of other initiatives that are, I think, in the same space, and I think have the possibility of really impacting how we do finance and making it more efficient. Okay, so I'm getting kind of near the end of my presentation. I want some time for questions also. But let me give you kind of my vision of what this means for the future. And then I have a few more applications, and then I'll be done. So I actually think of the internet in 3 stages. So I've been using the internet since 1981. It was only generally available outside academia in the mid-1990s with the World Wide Web. But the first implementations were basically to draw content. So New York Times, they took their newspaper and just dumped it online. Wikipedia was started, where you could just draw content. That's the first wave. The second wave is social media. We're living that right now. Twitter, Instagram, Facebook, ... Okay, so it allowed people to connect to larger groups of people than was possible in history. So unprecedented number of connections. So the third has to do with payments and what the implications of that actually are. So I call this machine-to-machine payments, and it turns out to actually pay for something on the internet is not so easy. So think of using a credit card. Well, there's a hefty fee that's associated with that credit card, which you pay for indirectly, or part of it at least. It's not secure. And on how many online firms have been hacked in terms of the credit card information. It's also not feasible to use for very small transactions. And also, it's one way that you actually pay. You can't get paid. So there is a current wave of fintech that is trying to disrupt those payments. And that wave is mainly coming from China with WeChat Pay and Alipay. China is way ahead of the US or the UK, way ahead. So they did 12.8 trillion of transactions digitally last year with things like WeChat Pay. The US, 50 billion. So China's really leading this. I argued that these people are temporary. A lot of the fintech that we see today is fleeting. It's just new middle people taking a piece of the action, and it's possible they're going to be disrupted with distributed ledger-based payment system. So, so basically, with the internet structure we've got today, and it's very interesting that when this was coded up in the early 1990s, they just assumed that there would be a digital currency. So the first digital currency ideas came out in the early 1980s. So it was reasonable, like 10 years later, to extrapolate that there would be a digital type of currency, and they built it into HTTP 402. You've all experienced a 404, website not found. This is 402, you probably don't know, but it's there, and you can look it up. And it is a facility that essentially allows for micropayments. So the recent wave of cryptocurrencies make this feasible. And what does it make feasible? It could be as simple as some of my students hopping into, let's say, an Uber, heading to the pub, and they get into the Uber, they do a survey or two, they get paid, and they pay the Uber with that money. So they're able to earn a little money while you're sitting around in effectively a taxi to pay for the taxi. So you're actually giving something up, your time, obviously. They're also giving up some of their information, which is valuable, and they're being paid for it. So this happens instantly, and this is an example of machine-to-machine payments. Think about email. So email, very inefficient system because it's free. And anything's free, people will abuse. So at at Duke University, I know that right now, 2/3 of the emails that come into the Duke servers never go to an inbox. Okay, I'm not talking about your junk folder. I'm talking about they never hit your inbox. 2/3. So spam constantly happening. So what if you change the model and you charge for an email and make the price pretty low, like 1/10 of a cent? So 1/10 of a cent puts the spammers out of business. But it also has a number of intriguing possibilities. So my inbox is at the top. It's got my family, my friends, my work colleagues. So in the future, they have to pay a small amount. But there's a lot of other people that would like to get to the top of my inbox that are not spammers. And indeed, I might be interested in what they have to offer me. So I'm going to set a price to get to the top of my inbox. Let's say $100. And if I open the email, $100. If I click on some link, $100. All of this is seamless. All of this is possible. Okay, so effectively, you are monetizing yourself. And of course, the same idea for the internet. Again, the internet is free for most of it, and it's constantly under attack, denial of service attack. What about a small fee? Okay, so this opens up many different possibilities of actually monetizing stuff that isn't monetized today. So your kid is in middle school, and they've got a project where they do a video, and it turns out to be a remarkably good video. It's posted on YouTube. It gets 3 million downloads, and you get nothing. So think of a different model where to download this video is going to cost 1 cent. That's no big deal. I'm willing to pay that. 1 cent. 1 cent times 5 million, that's a lot of money. You know, it's a down payment for college tuition. Okay, so this technology allows for the monetization of content. Right now, content is basically free on YouTube, on Facebook, and it's really hard to make any money off of it. This technology allows you to do this. I'm very negative on Google and Facebook, and have been for a little while. So their business model is going to be disrupted. So this is an example of some Google AdWords. So I'm in Dallas, and some truck, dents my car. So I decide to sue. I do a search for Dallas truck accident lawyer. A lawyer's name comes up, and I click on that. That lawyer pays Google $425.70. Okay, so Google is collecting all of this stuff. There's a different model where I get that money directly. So Google and Facebook are basically probabilistically trying to figure out who you are and your preferences, and then they will basically sell that information to advertisers, and the advertisers pay Google and Facebook, and ads are served to you. That's their business model. So think of a different system where you have your own profile. So it might be that you are looking for a new car. So you've got a space where you put your preferences in. Looking for a new car, thinking about whatever, BMW, Mercedes, and Audi, something like that. And then all of a sudden, into your inbox comes these offers. You come into the showroom at your convenience, and we will transfer $1,500 to your account. Okay, instantly. Okay, not check is in the mail. Instantly with this technology. So essentially, Google makes about $100 per user a year. Beware the average. Okay, that that is over all of their users. For the people in this room, it's probably more like $5,000 to $10,000. Okay, so think of that money going into your pocket. It will. Your information is your information, and you should be able to sell it if you want to reveal it. If you don't want to reveal it, fine. So again, this model is a bad model. Think of this technology as a technology where transactions costs are driven close to zero. Because remember I said, we go into the showroom, 1,500 is transferred immediately in real time. So this also disrupts things like, think of everything as pay for consumption, pay for view, to the extent that let's say you're watching a movie. You don't pay for the movie in advance for the whole movie. You don't subscribe to anything. You're paying in real time. So if you watch only 5 minutes of the movie, you pay for 5 minutes of the movie. That's it. Okay, so it could be a cell tower where instead of the current sort of mechanism with cell phone providers, people invest in a tower. You have 10% of the tower. Somebody drives by. They use the tower. A micropayment is made. That payment, your share, is transferred into your account as the owner of the tower. This is what this technology allows for. Okay, to finish off, I've just got a few applications. You're definitely familiar with this one, the Brexit ballot. So voting is an obvious application of blockchain technology. If we had blockchain-based voting, Brexit would never have happened. And very simple. The younger people, they were very pro-Remain. And we also knew they weren't going to vote. And you ask them why. So, well, why do I have to go to a polling booth? Why can't I vote on my smartphone? Well, this is exactly what you can do with this technology. You get a token, and that allows you to cast the vote. You can't sell the token. You have to prove that you're the owner of the token with a thumbprint or something like that. And the token expires after the election. So a very straightforward application. Internet of Things is basically wide open for hackers. So somebody can go into my Nest and jack the heat from 20 to 40. So blockchain-based technology allows for essentially only me or the people I permission to change the temperature in my house. This is more serious as we move to self-driving cars. It might be uncomfortable for the temperature at my house to be 40 degrees, but it's way more dangerous for somebody to hack into my self-driving car and take it over. So again, blockchain provides the possibilities here. I'm sure in the UK, there's a big problem with opiates, just like in the US, but the US is just a terrible situation. I'm not sure actually how it works here, but you could literally get a prescription at an office and then steal the pad of paper from the doctor's office, forge some scripts, and then go collect 50 different bottles and then go sell them. This is really like a system that is really no different than in the 1920s, again. So again, think of a doctor providing a token to you, and you can basically, that gives you the right for the prescription. You go to any pharmacy, you can spend it once, you can't transfer it to anybody else, it expires, and on top of that, there's a ledger that shows all of the doctors, how much they're prescribing, and you yourself are also in that ledger for the regulator to actually watch. So a very powerful system. Medical records, another kind of application, any type of records. Often these records are single password protected, which causes obvious issues. So for the medical records, a blockchain construct would allow for, let's say there's 3 million patients, you have 3 million passwords. You can still be hacked, but it's just much more difficult to come up with 3 million passwords. And indeed, it allows people to give permission from one hospital to another to access these records. I know it's different in the UK with the national system, but in the US, you could go to one hospital like down the road from your main hospital, and they can't share records. You have to go through a long process. So this technology allows this to happen. Financial statements are, again, something that is a historical sort of legacy to do quarterly reporting. In the future, there'll be real-time reporting, the same information, except in real time. And there's some advantages to this because a lot of shenanigans go on at the end of the quarter to kind of hit the earnings forecast. Well, if it's real time, there's no incentive to do anything like that because people will understand that the numbers coming in are noisy and you won't necessarily have the same incentives. So the accountants are very keen on this technology. They will be winners. So they'll be implementing new kind of reporting systems. They're also in the consulting business where they go into companies and basically figure out how this technology could save them money. And also within the private blockchains, you need somebody trusted to verify transactions. PwC, Deloitte. We trust them anyways to sign off on the financial statements. They're just ideally suited for this new type of business. Okay, my last example is FedCoin. So 79% of the value of U.S. currency is in $100 bills. It's really difficult in the U.S. to find anybody that has a $100 bill in their wallet. And you go to stores, retail outlets, they have this sign that says, no $100 bills accepted. Okay, so it seems a bit of a contradiction that most of the value is in these notes that people don't actually hold, and you can't use them even if you hold them. So the real story here is El Chapo. So the drug lord, the Mexican drug lord, this is his stash, 200 million in $100 bills. And you can see some 500 euros there and other stuff. So basically, the cash is largely used for crime. So again, when you go to a national cryptocurrency, like I call it FedCoin, you solve that problem. You also solve these other problems like getting around the VAT by paying cash. Can't do that. There's no cash. Okay, and indeed, that insight alone has got almost every central bank interested in this technology, including Bank of England. Sweden, less than 2% of transactions are done in cash. So no big deal for them to switch to a blockchain-based national cryptocurrency. So we will definitely see that. Okay, my last slide. I've actually got something from the UK. And we've talked about some of this stuff. We talked about voting. We talked a little bit about cryptocurrency, money transfer. But there's all this other stuff that we didn't talk about that's kind of obvious. So, like to me, the chance that there's going to be paper cash, even in the near future, so the children born today, by the time they get a job, there's not going to be any paper cash. It'll be for people that collect coins and notes. It'll be a historical artifact. Okay? So it's also true for other things, like a passport. A paper passport? You got to be kidding. We know that's not going to exist in the future. And people forge these passports. So if we had a blockchain-based sort of system, you identify who you are. Again, it could be a scan or fingerprints, and that's it. The ledger is consulted. You are who you basically are, and we're done. Like when I travel, I'm always stressed out that I forgot my passport. I did that once, actually. It was a disaster. Or I lose it. And I've also lost the passport many years ago. It's not easy to get my Canadian passport back. Given I live in the US, I have to travel to Canada. It's a nightmare. So again, this technology allows for a much more efficient sort of system. Is it like a diamond up there? So it's a simple idea that in the diamond industry, there's an issue with the blood diamonds. So the clean diamonds, you laser in a code that you can't see, but that code goes into a blockchain. The diamond's received. The code is checked on a blockchain construct. The diamond is clean. So there's all sorts of applications like this. A power application, I could go on and on. Essentially, this is a way of using blockchain technology to share, let's say, solar power between, let's say, neighbors. So we're lucky that we've got a power grid here, but for much of the world, there's nothing like that. So if you had a solar panel, sometimes that energy is wasted, and sometimes you need some extra energy. So you set up a local grid, have it blockchain-based, and people essentially trade their surplus power. You don't need a utility to actually do this. Okay, so to finish up here, this is, I think, a significant innovation. Institutions like banks are already under attack. They are very thick middle people. So they're already under attack because of the P2P sort of lending and borrowing that's growing, where I can get a much better deal from my peers than the bank on both sides. So they see that in terms of the finance function, in terms of payments, that they are at risk with this technology. It's also the case, and I didn't really go into this, that there are 2 billion people in the world that are unbanked. And there's no chance of them getting a credit card or a debit card. They're unbanked. So this technology essentially allows everybody to have a bank in their pocket. You need a smartphone. That's what you need. So you think about that, putting 2 billion people into the system. So now they're able to transact on the internet. That's a big idea. Okay, the last thing, and I think I've said the last thing about 5 times, but the last thing, I want to put this idea in your head. The Royal Mint Group has got this idea. They're partnering with the Chicago Mercantile Exchange. And what they're going to do is to take 1 million ounces of gold, dump it into a vault in London, and then issue cryptocurrency backed by the gold. So 1 RMG, think of it as the equivalent of an ounce of gold. Okay, so it's going to be audited, and we trust the Royal Mint Group. Okay, so that coin will be fully collateralized, and it will have the volatility of gold. So think about the future. Think about your wallet of the future. Your wallet of the future isn't the wallet of today, that you've got credit cards stuffed in there, driver's license, and your Oyster card and cash. No. The wallet of the future is a smartphone, which has also got all the critical information, your passport, your driver's license, your cash. But on the cash part, think of your wallet. You open it up, and you've got pounds. You've got maybe a cryptocurrency like Bitcoin. Maybe you've got RMG, gold. So you go to your local grocery store, and you can pay with whatever you want. So you can pay in gold. Maybe the store doesn't want gold. Well, there's somebody else out there that instantly will take your gold and transfer it into something that the store actually wants. So maybe you see where I'm going here, that this idea of collateralizing a cryptocurrency means that you can collateralize almost anything. So the gold idea I think, will put out of business the ETFs that are linked to gold. GLD is the largest one. Why would I buy the ETF and pay the fees when I can exactly do the same thing a lot cheaper? And indeed, I don't need to buy $1,000 worth. It could be $5 worth. So this idea of having a wallet with all of these tokenized assets basically takes us into full circle. In the history of money, before money, there was barter. And barter was really inefficient because the two parties had to basically want the same thing. It was very difficult to match up. And that's where money actually was born, to make that system more efficient. This technology, tokenizing assets, cryptocurrencies, instant transactions, very low fees, it makes it possible for us to see a future that could be barter. Okay, so these are big ideas. So in my course, as I said, we talk about blockchain in general. There are many possibilities here, and we're just at the beginning, So hopefully I've given you some of these ideas. I'm more than willing to take some questions. There's no clock here, so I have no idea how long I went. What time? Quarter? Oh, it went 15 minutes too late. Sorry about that. Yeah, I'm more than willing to take any questions, and I'll hang around a bit also on this. So are there any questions? Yeah.
Isn't it fundamentally the case the problem with blockchain as they are today is that they're relatively inefficient compared to other transactional ways of databases?
Yeah.
And that you can see it with what's happening with the Bitcoin and the Ethereum blockchains. As soon as the number of transactions increases, the efficiency drops massively. And so is that not a fundamental problem?
Yeah.
In taking blockchain into a transactional world?
Well, it's a fundamental problem for, let's say, Bitcoin right now. It's less of a problem for Ethereum right now. So the idea is just the number of transactions per second with the current technology is limited. But they've already got, I will refer you to something like Lightning Network, which is a second layer that potentially can mitigate some of these small transactions, increase the throughput, and even further, I'll take it even further, that I don't believe the Bitcoin or Ethereum are scalable. So what I'm talking about is other cryptos that could have incredibly high throughput, like FedCoin, that you don't need to worry about transactions per second. Goldman Sachs is basically, they bought this firm called Circle, and their idea is to collateralize, not with gold, but with the US dollar. So basically create a crypto that is exactly linked to the US dollar. There's one out there already called Tether, but people have difficulty trusting it because it's based in like Nevis or somewhere like that. People have more trust than Goldman, I guess, than Tether. And exactly, they basically determine the rules, and they could have very high throughput for that. So it is an issue. I agree. It is an issue today. Is it an issue that's insurmountable? Probably not. Again, remember, this is kind of early days for this. Yes?
How do you envisage the solution cycle then? I looked at, for example, the bottleneck of proof of work for Bitcoin,
Yeah.
blockchain, and obviously Ethereum gets around that by proof of stake, which has its own issues.
Right.
Without, and obviously, those second layers with bigger blocks and stuff, I see other issues with that. While being able to maintain a sort of completely distributed nature of blockchain technology without going back to sort of having FedCoin be centralized or something, how would you envisage getting over problems of proof of work, proof of stake? Do you know what I mean? To kind of get the kind of throughput that these have right now.
Right.
Or even kind of throughput that, we talk about like FX on a global scale.
Right.
Think about how many transactions there are on the FX space.
Right. Yeah, so what I described for Bitcoin is called proof of work, where you find the 18 zeros, right? And it's very inefficient in terms of power. Ethereum is the second most important blockchain out there for cryptocurrency. And Ethereum has got the advantage, you can actually run a computer program or a smart contract within their blockchain. So it does something that Bitcoin's blockchain doesn't do. They also are proof of work right now, but they plan to transition to what's called proof of stake. So instead of all these random miners competing, essentially the people with the largest holdings of Ethereum have the highest probability of being asked to essentially mine the block. So the power consumption is dramatically less when you actually do it that way. And if you've got a lot of Ethereum, it's in your best interest to do a good job, right? So it's incentive compatible. There are at least a dozen other consensus mechanisms. And I've got a whole lecture that I do on consensus. So it's interesting, again, I said that blockchain technology is a technology. There's many different ways to approach it. And it's just not clear that there's going to be one consensus mechanism. Bitcoin will always be proof of work. Right? That's not going to change. Ethereum is changing. And it's not clear what we actually head towards. And I think kind of linked to the other question, the scalability is going to be very important in how we do it. If it's a private blockchain, then it's just the permission people that can add the blocks. We don't have the bottleneck problem whatsoever. But it's hard to imagine kind of a world version, as you said, with all these billions of FX transactions happening all the time. Is there like an IMF sort of chain where you trust one kind of international institution to handle all of this? I don't know. We'll have to see.
Yeah, I take your point. It seems to me that a lot of the solutions either involve getting rid of the distribution aspect. As soon as you have kind of trusted parties, if you look at a lot of stuff that say R3 consortiums do,
Right.
With, as you say, with these private blockchains and trusted parties and what they call it, notary nodes and stuff like this. It seems to me like a lot of those systems, I see the strength because it gets around like the bottleneck of it. But you could come up with, using existing non-blockchain technology, come up with systems that did the same thing.
Yeah. So your point is a super important point because, as I said in my course, the students have to present a blockchain-based idea. And the first question is, do we really need a blockchain for this? Because given all the hype of blockchain, some companies have changed their name to insert blockchain into the company name, then stock goes up in value, even though they're doing nothing in terms of blockchain. So I think that if you decide to go to a public blockchain like the Bitcoin blockchain, that means that there's no trust. So you don't need to trust the other nodes. Everybody's incented to do the right thing. So you don't know who they are. And it could be anybody. So there's no trust. But the cost of having no trust is enormous in terms of that computing power and the energy being used with the proof of work. So in many situations, we already trust. Like, for example, we already trust our banking system and the Bank of England, the Federal Reserve. That already exists. So it's not obvious that we need to go to a system that basically takes them completely out of it. So think of it as a continuum, where on one extreme part, you've got, let's say, the Bitcoin blockchain, where there's no trust. The other extreme part is what we've got today. And there's a lot of room in the middle where you inject some trust. Maybe it's not fully distributed. It can be decentralized, but not fully distributed. But there's some sort of compromise for it to match the economic problem that you're dealing with. So that some people just pull the trigger, say, well, this is a great innovation for whatever space, and we don't need trust. It's, well, okay. Why is that important? Why is that a reason for me to invest in your venture? I'm afraid not. Yeah, indeed. You need to beware of the hype. There's all these ICOs, initial coin offerings. Probably 90% of them are not going anywhere. Right. So they're The business models are flawed. They're just jumping in because you jump in when stuff goes up in value. Yeah, so I'm pretty negative on that. I've got a presentation called The Wild West of ICOs, if I had more time. Any other? Yeah.
For public, for smart contracts that are on the public blockchain, are they in any way backed by any legal system?
So that is like a major issue in terms of enforceability. So that that question depends on the jurisdiction. So there are certain jurisdictions in the U.S. where they are enforceable, and most of the jurisdictions they aren't. So that's definitely an issue. So again, this is kind of right at the beginning of this process, and the legal and regulatory aspects are important. It's almost impossible to go to sort of case law of the past because this technology didn't exist in the past. So essentially, we're working it through. But excellent point. Yes. So what Goldman's going to do is, it's actually not 100% clear. They've just announced the kind of collateralization of a crypto. So I'm not sure if they're using an existing crypto or, and what I mean by that is you could take, let's say, one Ethereum and then divide that into 1 billion pieces. Each piece is worth next to nothing, but it's got a private key that you could associate with the US dollar. That's this idea of tokenization. So a token is something that doesn't have its own blockchain. A coin, a cryptocurrency coin, has its own blockchain. So Ethereum and Bitcoin have their own blockchain. So it's not clear how they're actually going to do it, but so Tether is basically a token. So I suspect they'll do the same thing. Okay, cool. Okay, thank you. And I'll hang around if there's other questions. Thanks.